equipment needs to be rated for the maximum fault current it might encounter. This ensures the equipment can safely withstand a fault condition without failing, causing further damage, or creating a safety hazard. When assessing fault current, it's crucial to consider both line-to-line and line-to-neutral faults. A line-to-line fault occurs when two energized conductors come into contact with each other, while a line-to-neutral fault happens when an energized conductor contacts the neutral conductor. Generally, the line-to-line fault current is higher than the line-to-neutral fault current. This difference arises due to the impedance in the fault current path. The line-to-neutral fault path often includes the neutral conductor, which introduces additional impedance compared to the direct path between two energized conductors in a line-to-line fault. Because the line-to-line fault usually produces a high fault current, the equipment must be rated to withstand this high level. This ensures that the equipment can handle the worst-case fault scenario. To determine the appropriate fault current rating for equipment, you need to perform a fault current study. This study involves calculating the potential fault current at various points in the electrical system, considering factors such as the utility source impedance, transformer impedance, conductor impedance, and motor contributions. The fault current study should consider both line-to-line and line-to-neutral faults to determine the maximum possible fault current at each point. The equipment selected for each location must have an interrupting rating or withstand rating that is equal to or greater than the calculated maximum fault current at that location. Interrupting rating applies to devices like circuit breakers and fuses, which are designed to interrupt the flow of fault current. Withstand rating, also known as short circuit current rating, applies to equipment like panel boards, switchboards, and motor control centers, which are designed to withstand the mechanical and thermal stresses of a fault current for a short period. Several factors contribute to the magnitude of fault current. These include the available fault current from the utility, the transformer impedance, conductor size and length, and the presence of motors. The utility's available fault current is the maximum fault current that the utility can deliver to the service entrance of the building. This information is typically provided by the utility company. Transformer impedance limits the amount of fault current that can flow through the transformer. Lower impedance transformers allow for higher fault currents. Conductor size and length also affect fault current. Larger conductors have lower impedance, allowing for higher fault currents. Longer conductors have higher impedance, reducing fault currents. Motors contribute to fault current during a fault condition. When a fault occurs, motors act as generators, feeding current back into the system. This motor contribution can significantly increase the total fault current. The calculation of fault current involves several steps. Firstly, you need to obtain the utility's available fault current. Secondly, determine the transformer impedance from the transformer nameplate. Thirdly, calculate the conductor impedance based on conductor size, length, and material. Fourthly, calculate the motor contribution based on the motor horsepower and type. Fifthly, combine all these factors to calculate the total fault current at the point of interest. There are several methods for calculating fault current, including point-to-point calculations and computer-based modeling. Point-to-point calculations involve manually calculating the fault current at each point in the system. Computer-based modeling uses software to simulate the electrical system and calculate fault currents automatically. After calculating the fault current, you must select equipment with an appropriate interrupting rating or withstand rating. The interrupting rating of a circuit breaker or fuse must be equal to or greater than the calculated fault current. The withstand rating of equipment like panel boards and switchboards must also be equal to or greater than the calculated fault current. If the available fault current exceeds the interrupting rating or withstand rating of the equipment, you must take steps to reduce the fault current or replace the equipment with appropriately rated equipment. Several methods can be used to reduce fault current, including using current-limiting fuses or reactors, increasing conductor impedance, or using transformers with higher impedance. Current-limiting fuses are designed to quickly interrupt the flow of fault current, limiting the magnitude and duration of the fault current. Reactors are inductive devices that are installed in the electrical system to increase impedance and reduce fault current. Increasing conductor impedance can be achieved by using smaller conductors or longer conductor runs. Using transformers with higher impedance will also reduce the fault current. It is important to consider the coordination of overcurrent protective devices when selecting equipment and reducing fault current. Overcurrent protective devices, such as circuit breakers and fuses, must be coordinated to ensure that the device closest to the fault opens first, minimizing the impact of the fault on the rest of the system. Coordination studies involve analyzing the time current characteristics of the overcurrent protective devices to ensure proper coordination. The National Electrical Code, or NEC, provides requirements for the selection and installation of equipment based on fault current. NEC Section 110.9 requires that equipment intended to interrupt current at fault levels be rated for the available fault current at the line terminals of the equipment. NEC Section 110.10 requires that equipment be selected and installed to withstand the available fault current without creating a hazard. NEC Article 240 covers overcurrent protection and provides requirements for the selection and coordination of overcurrent protective devices. Understanding the concepts of fault current, interrupting rating, and withstand rating is essential for ensuring the safety and reliability of electrical systems. Properly selecting and installing equipment based on fault current requirements helps protect people and property from the hazards of electrical faults. Regular fault current studies should be conducted to ensure that the electrical system is properly protected. These studies should be updated whenever there are changes to the electrical system, such as the addition of new equipment or changes to the utility service. In addition to the NEC, other standards and guidelines provide information on fault current calculations and equipment selection. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. These standards provide detailed guidance on performing fault current studies, selecting equipment, and coordinating overcurrent protective devices. Consulting with a qualified electrical engineer is recommended when performing fault current studies and selecting equipment. An electrical engineer can help ensure that the electrical system is properly protected and meets all applicable codes and standards. Remember that electrical work can be dangerous, and it should only be performed by qualified individuals. Always follow safe work practices and use appropriate personal protective equipment when working on electrical systems. Failure to do so can result in serious injury or death. In summary, always rate equipment for the higher of the two calculated fault currents, line to line or line to neutral. This ensures the equipment can handle the worst-case scenario and maintain safety and reliability. Regular fault current studies, proper equipment selection, and adherence to the NEC and other relevant standards are crucial for a safe electrical system.